Give a sense of how monstrously large the number tree 3 is.
Okay, well, I think the best way to talk about tree 3, there's some technical definitions that require some expertise in a subject called recursion theory. But one way I look at it is this: tree of 3 is so big that you can't even prove it exists. Uh, that you can't prove it exists even in a strong system like piano arithmetic.
If that were true, that would indeed be mind blowing because any finite number can be shown to exist depending on your definition of exists.
I'm sorry. I misstated this. You can't prove it exists without using 2 to the 1 trillion pieces of paper. That doesn't mean that it's bigger than 2 to the trillion. It's incredibly bigger than that. I'm saying even with 2 trillion pieces of paper, that makes sense. You're not even proving it exists.
Right.
I don't know how if that helps a lot, but and also a considerably stronger system than piano arithmetic. The statement I made is correct.
How does it compare to Graham's number?
Well, if I remember Graham's number, I think it's kind of not noticeable.
Yes. It's minuscule in comparison. Epsilon.
Now you can play this artificial game in many ways, but this is a particularly elegant one that is mathematically very friendly. If you remember the definition.
Yeah, what is the definition of that number?
Yeah. Okay, you look at finite trees. Okay, first there's an infinite fact that's behind it. And then you think of this as a finite form, so to speak. And the infinite approximation is you have an infinite sequence it goes back to J.B. Kruskal. You have an infinite sequence of finite trees with 3 colors if you want. I do it with 3 colors. With 3 colors on the vertices. Each vertex has one of the 3 colors. You have an infinite sequence of finite trees. Then one of the trees is a part of a later tree, and part of means there's a color preserving embedding that's inf preserving. It's a slightly technical notion, but it's the obvious notion of homeomorphic embedding. There's a whole combinatorics that was well known of finite trees and how they fit together and what does it mean, but isomorphism and all that. Okay, so once again, given any infinite sequence of 3 colored trees, finite, one of the trees in the list is embedded in one of the later ones in the list. This is a famous theorem of J.B. Kruskal. And I noticed, or maybe I wasn't the first to notice, but I made the first to do something with it. I noticed that this proof involved looking at all possible infinite sequences of trees, uncommonly many, and this proof was so far from being local. You might expect you just locally figure out this piece. It was so unusual, this J.B. Kruskal proof.
Yes.
And I proved why it was so crazy, so strange. I proved that Kruskal's theorem can't be proved in systems you'd expect it to be proved. Now, this is still nothing like ZFC. The ZFC incompleteness is something entirely different, a different level. But this is a micro incompleteness, so to speak. And I kind of proved that you need uncountable sets to prove this Kruskal thing. Okay? Now, how do you approximate the Kruskal thing? Because after all, it's about infinite sequences. Well, it turns out that from the things like the compactness theorem, well known in mathematics, you can show that if you put a bound, if you say that the ith tree has at most I vertices, the ith tree has at most I vertices. So you put a bound on the growth rate of this trees. Then you can find one of the trees is embedded in a later one, but you can even find a stopping place. You can even put a bound on how far you have to go up in order to know that. You follow me? In other words, you have to go a long way. So how far do you have to go up to get this? That's called tree of three. Tree of three says, how long do you have to go on like this so that one of them is embeddable in a later one? As long as the I tree has the most vertices and we have three colors. That's what tree of three is. How long do you have to go up there? Now, from general mathematics, you can prove from Kruskal's theorem, which is about the infinite sequences, you can prove that there is a bounding place. There is a place so high that you can get there. So if you know Kruskal's theorem, you actually know tree of three.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org. Okay, now what does this have to do with the relationship between infinity and the finite?
Well, this says that there's really a very close connection between the really big finite, the outrageous finite, and the small infinite. The smallest infinite is just omega, the size of the natural numbers. That's the smallest infinity. Cantor has higher infinities, like the real number line and all that.
Yes, I have a video about that.
Yeah. So the smallest infinity is very closely associated and approximated by the outrageously large finite. And we see this pattern over and over again. Now, I actually took this even more crazily, put on my crazy hat, okay? I said, suppose I'm a finitist. I'd say, okay, only finite things, maybe big things, maybe not even, I don't even like big things. If you're an applied computer scientist, you don't care about gigantic numbers. It's too impractical, right? Too impractical. You only care about things like a quadrillion or something is all about the most you could stand for. So what if I put my finitist hat on and I say, okay, all of mathematics I'm going to make finite. I know it's not finite directly, but I'm going to find finite approximations. And thesis, all of mathematical ideas are already represented in the finite. Pretty outrageous idea. In other words, all this real number stuff, all this partial differential equations, even all this set theory stuff, large cardinals, it's all fundamentally finite.
But
this is my crazy hat.
Yes.
A finitist hat. And in fact, the book, Embedded Maximality, has a section on purely finite forms, which shows, in a sense, that all these large cardinals beyond ZFC can be thought of in finite terms.
Now, let me ask you this.
Yeah.
What about ultra-finite terms?
Okay, you talking about ultra-finitism? Well, that's the point. That's the idea that you shouldn't go past very small numbers. That already 2 to the 100 is absurd.
Mm-hmm.
That's ultra-finitism. Yes, that's part of the crazy hat.
Interesting.
If you really want to push this really hard, all mathematical adventures can be properly imitated or realized in a computer screen, that level of detail. In other words, pixels with colors. Everything there is just pictures. That's already more than enough. Now, we kind of know that this is true in some sense because the human mind is thinking about things. I'm looking at this screen and I'm looking at everything. Everything I think about, my work, my pace, this is all well within the computer screen's size of information, which is only X bits, where X is, from the 1,000,
Sure.
whatever, right? So this is actually the most radical. And now the question is, all these fancy mathematical ideas we have, including large cardinals in ZFC, how do we actually say that we've actually properly represented them in a picture? I believe this can be done. And I think what's in my book is nowhere near that powerful, but it does suggest some things.